Today I'm going to talk about some various secret sharing schemes that I looked at for a recent end of semester project in cryptography. So, secret sharing, in its essence, is a way of keeping a secret safe and secure while distributing information about it in such a way that a certain amount of that information has to be aggregated together in order to recover the secret. So you're keeping your secret safe, but you're also putting in some redundancy so that others can recover your secret if, say, an emergency arises or you forget it yourself. So the question is, how do we do that? Because it's not entirely clear the best way. Some possibilities are that we could just directly share the secret with our friends, but obviously that's not secure. It is worth noting that it is convenient for them to recover it. Granted, they might act maliciously, but they can recover it very easily. Instead, we might distribute, say, letters and a password to friends, right? Everyone gets a piece of paper with a letter or a number on it and the password. And in theory, that's a little bit more secure because, say, if they don't know the ordering, but then it's not easy for them to recover it. And if somebody loses it, well, then you have to start guessing. And then the other trivial option is to just not share anything, which is the most secure you can be and the least convenient because, well, nobody can recover it. So we want to maximize the security both in simple terms and in cryptographical terms, as well as the convenience. How easy is it for my friends to recover my secret? And we might ask how we can do this in math. What object can we use that has this property? Well, you actually don't even need math. One way to do this is to write down your secret using spaces and distribute them out to your friends, which is an example I did here. If one or two of my friends, right, so give each one of these out to your friends, through three different people, one of them or two of them will not define the secret. If you have all three, you can get it. And obviously the answer is the first six digits of pi. So the question at the bottom here, one solution, and there's many, but one way is to use polynomials. And that's the basis for Shamir's secret sharing scheme. In his scheme, which was developed in 1979, you choose your secret, A0, a prime P, a number of shares N, and the threshold K. So the number of shares, the N here is just how many you manufacture, which has nothing to do with the security. You can generate as many shares as you want. The security arises in how big you choose K to be, and is bounded by N. So I suppose N does impact the security a little bit in an implicit way, but the idea is that K determines how many of your friends have to together to reveal the secret. We'd want to choose that to be high for the maximum security. Then the dealer, whoever owns the secret, would construct this polynomial of degree k minus 1, where the coefficients are randomly chosen, and they're all non-zero. So you have to have every term in the polynomial. The dealer would then distribute a number of shares, n, and k. So you need k for your shareholders to determine the secret, ideally, right? Because you want them to know how many of them need to come back together to reveal it, so they're not just guessing. And these points are obviously points in the polynomial. Now, given any subset of k shares, they can compute this sum product. And this is Lagrange's interpolating formula for x equals 0. Because if you look closely, the secret is the y-intercept when x is 0, the polynomial. And if we want the secret, we actually don't need the whole polynomial. We just need the y-intercept. And this formula would give us that. Now, this is why it's important that all the coefficients are non-zero, so that there's so that we can find the y-intercept. If you notice, I didn't mention the prime, and that's because the way this is written isn't the full scheme that Shamir proposed, and this is why. Because remember, the shareholders have to know k, so they know k minus 1, so they know the degree of the interpolant. Well, if you know the degree and you start plotting points, it's pretty easy to determine the polynomial, especially if there's a lot of points, if you get a lot of leaked information. So it's not a good idea to use real value polynomials. In fact, if you chose your secret, if you chose your x values in the shares, so x1 to xn, if they're consecutive integers, then you can actually show that if you have 3 shares, the threshold of 3, and you have a sequence of consecutive x values, you can narrow down the choice of the last coefficient, the polynomial, which would be needed to recover the secret, to only like 86 choices out of a theoretical infinite number of coefficients. And so we really don't want to use real value polynomials. And this is where the prime comes in, because you can run your polynomial through a finite field. Specifically here, we're using ZP for some large prime. And so I took this polynomial and did 100 or so points mod a large prime, and this is the result. So on the right, there is absolutely no way you could determine the polynomial by looking at that picture. And so geometrically, like graphically, we would expect a mod P polynomial to be secure, and it is. Shamir's secret sharing scheme is secure if you have a polynomial run over a finite field. And ZP isn't the only choice, but it does make the most sense. I looked at some ways you can modify this, so you could use Newton's divided difference. This is a way to calculate the shares differently. However, you get the same polynomial because if you have, let's say, k data points, that will uniquely define a polynomial of degree k minus 1, provided the points that you use are distinct. That's a theorem, you can prove it. So Newton's divided difference gives you the same polynomial, but the way that you do it makes it a little bit more computationally friendly in the sense that you can add shares on without having to regenerate the polynomial. If you change it a little bit in Lagrange's formulation, you have to do a lot of work. And Newton's divided difference makes that a little bit easier to do. I also looked at using Chebyshev nodes. This was more of a slight digression for the report, and this wouldn't work. I don't believe this would work for the case where a finite field is used, specifically ZP, because you could have coefficients that are not integers in the field. So I don't suspect this would work. If you use the real value polynomial, it might be slightly beneficial. The only advantage I can see of using Chebyshev nodes is that it would eliminate the runge phenomena happening at the endpoints, which would be common if you used a high degree polynomial in equally spaced nodes. So perhaps if your degree was high enough and used enough nodes, your polynomial would exceed your computer's computational precision, say, but I don't know if that's an issue. It was just something I thought of and included it. Now, there are some issues with Shamir's secret sharing scheme. First, the shareholders could contribute false information. So if they throw their shares into the pile, say they all come together, they could record other people's shares and then go back home and recover the secret, while their friends would have a wrong share and wouldn't get a secret or wouldn't get the unique secret. So that's an issue. The other issue is that we don't know if the dealer is honest, in that maybe they don't want to reveal a secret, but they want to look transparent, and we would want a way to fix that. We also don't know if the shareholders received valid shares. So this kind of goes into the second point. How do I know as a shareholder that my share comes from the polynomial without revealing the polynomial? And this is solved using verifiable secret sharing and publicly verifiable secret sharing. There's a few schemes to do VSS. One of them is Feldman's scheme. So you give out more information, and it involves checking that your share is the discrete logarithm of a public value that the dealer distributes. That's kind of like a broad picture. We can, and so with VSS, you as a shareholder can verify your share came from your polynomial. With publicly verifiable, anyone can verify anyone's share. And this is using VSS combined with some public encryption scheme like Elgamal. And so you can make sure that all the shareholders have a legitimate value because they can publish information in a public key system. It's way more complicated than this, but this is a very broad picture. There is another scheme that is not based on interpolation, which I didn't know about until I was looking this up. It's called Asmuth-Bloom. And it's based on the Chinese remainder theorem and the uniqueness that's involved with the solution. So you would take your secret S and your number of shares and your threshold, and you would construct a sequence of pairwise coprime positive integers. So every term in the sequence is relatively prime to every other term in the sequence, and it satisfies this product property. Now the dealer would then choose alpha and compute and keep secret some y. They would then distribute shares where the yi term is congruent to their secret y mod some modulus. So the y and the m are distributed each to the shareholders. And if you have k shares back together, they can determine y, because this sets up a system, a classic system for the Chinese remainder theorem. And once you determine y, then you can do y mod p. Because if you do y mod p, the alpha p term is 0, and then you just get s. And p is a publicly known value, but you would have to know y in order to get s. So there are some attacks, which I didn't go into. There are some attacks on this. It's not perfectly secure. I believe there are some backdoors you can do into getting information here. But I thought this was just interesting as a scheme that doesn't use polynomial interpolation. And that is my presentation.